Well, you have all probably played on the merry-go-round when you were growing up, right? That's fun. You stand on the merry-go-round and your mother is standing there and watching, and you want to go faster and faster and faster. Your friend is standing on the other side and shouting, screaming, wants to throw a ball at you, and so on. And we talked briefly about this. So Earth is also rotating around its axis, right? We talked about the axis through which the Earth is rotating, and the axis is tilted to the orbital plane now at 23.5 degrees, and so on. What is the impact of being on a rotating planet? It is similar to being on the merry-go-round, except now the merry-go-round is a sphere, not a flat thing. So this is called Coriolis effect. Everything that moves on Earth feels the rotational effect, and if the Earth were to stop suddenly, we'll all go flying out. Because we are moving with the system, we don't feel it. If you go on the merry-go-round, you can stay on it and keep going round, but when you get off, what happens? You begin to feel dizzy and wobbly and so on and so forth if you stay too long. So let's imagine that the Earth was not rotating, Earth was standing still in the middle, and the sun was going around. In this case, let's say somebody was sitting at the North Pole, let's say Santa Claus, and he wants to throw a bag of chocolates at you sitting here on the equator in the Atlantic Ocean. We're looking at 0-degree longitude here, and this would come straight at you because Earth is not rotating. Whatever Santa Claus threw at you would reach you at the same longitude. He threw it here at 0-degree longitude. It will come straight to you, and if you look from the top, you will see that Santa Claus is sitting here at the North Pole and targeting you at sitting at 0-degree longitude on the equator. You can sit anywhere and Santa Claus would still reach you. The point is, if the Earth is not rotating, then things would move straight from anywhere to anywhere. There will be no effect. But now imagine that now we are on the real Earth, which is rotating around its axis. So here is the North Pole, and it's going from west to east if you are looking at the North Pole, let's say from above. And since in space there is no up or down, you can look from the south and it will still be going west to east, but now everything will be reversed because you are here or here. So Australians feel very different things than us. You still have trade winds, you still have monsoons, westerlies and polar easterlies and so on. But now what happens? Let's say Earth is obviously rotating once in 24 hours, which means every location on Earth is going around once in 24 hours. What is the difference? The difference is if you are sitting here at 0 degrees on the equator, then you have a large distance to travel in 24 hours. Right? So you will have to go very fast because Earth is a sphere. The circumference of the Earth is much larger near the equator than here near the pole. Okay, on the pole you would be just standing still because it's one point. So on the equator you will have to go something like 1600 kilometers per hour to cover the 360 degrees in 24 hours, whereas here it would be much shorter, maybe 200 kilometers per hour. What does this mean? That means when Santa Claus launches his bag of chocolates at you on the equator, he's going around at a very slow speed. As the bag is coming this way, it is traveling very slowly from west to east in the direction of Earth, but the Earth below is traveling faster and faster as you come towards the equator, because the locations towards the equator have to travel faster and faster to cover the distance 360 degrees in 24 hours. Okay, that means this is going east at a slower speed, Earth below is going east at a much faster speed, so the bag of chocolates is going to keep falling behind. Okay, I hope you can imagine that. So the actual destination is going to be off by 15 degrees in 1 hour if it takes from there to there just 1 hour. Okay, just make sure you understand it. Anything that is starting from here is going west to east at this speed, whereas here it's going at a much higher speed because it is traveling much larger distance. It's still 15 degrees, but since the latitudes converge towards the poles, the distance here between 15 degrees is much smaller because we are on a sphere. Okay, so you can look at this, look at it this way. You are going east to west, but at a very, very slow pace here, because let's assume he's not right on the North Pole, but somewhere just away. And as it travels, as the chocolate bag travels south towards you, the earth below is moved much faster than the chocolate bag, which is moving eastward at a much lower speed. So there is an easier way to remember it. There is the same thing that happens even if you're moving east-west. Okay, it's a bit hard to explain because you will need physics, you will need a force diagram and so on, which I explain on my YouTube channel. If you want, you can follow up. But another way to remember it is that in the northern hemisphere, everything will get detoured or deflected to the right of its direction of motion. Since the direction of motion here is southward, if you deflect to the right, it will go westward. If you throw something from the equator towards Santa Claus, let's say you are sending your list of wishes to Santa Claus and throwing a message bottle towards him, then you will be deflected to the right, which means you will be going eastward. Deflected to the right. Why? Because the bottle you are sending is moving west to east at a much faster speed than here, so this is going eastward very slowly, so this will go ahead of it because it started with 1600 kilometers per hour, whereas the earth below is only moving at 200 kilometers per hour. Okay, so just remember, things in the northern hemisphere gets deflected to the right of their direction of motion. So even if somebody is going from west to east or east to west, they will still be deflected to the right of the direction of motion. This is what you have to remember. And you have to remember, in the southern hemisphere, if you flip it and look from the south, everything will flip, so everything gets deflected to the left of the direction of motion in the southern hemisphere. Okay, you can do the same logic by starting at the South Pole, and you will see that everything goes to the left of the direction of motion, because you will be starting here, you are moving west to east at a slow speed, this is moving faster, so you will fall behind, so you will go to the left. Same thing. Okay, so now you can just use that knowledge to look at the winds again. Winds are trying to come from the sinking region here towards the equator, and Coriolis is pushing it to the right. So going south, pushing to the left, to the right means westward tilt. If you're coming to the north from the sinking region here, then you are pushed to the left, so you get southeasterly winds, you get northeasterly winds here. These winds are going northward and they get tilted to the right, so they become westerlies. They are coming south here, they get pushed to the right, so they become easterlies. And similarly here, push to the left, become westerlies, push to the left, become easterlies. So you end up with northeast and southeast trade winds, westerlies, westerlies, easterlies, easterlies. Very simple. Okay, so similarly, when winds rise and hit the ceiling and they're trying to go north, as we saw in the cells, same thing happens. So everywhere in the northern hemisphere you will be pushed to the right of the direction of motion, and to the left in the southern hemisphere to the direction of motion. Same thing happens in the ocean to the currents as well. As the winds pull to the west, they will be pushed to the north, and so on to the south here. Okay, so now you imagine something very curious. Winds are pushing it to the west here, to the north of the equator, so water will be pushed to the right of the direction of motion, which means towards the north. Just to the south of the equator, winds are pushing to the west, but Coriolis will push the currents to the south because it has to go to the left of the direction of motion, which means water is being pushed to the north on the northern side of the equator, to the south on the southern side of the equator. Wow! What just happened? If you push water at the equator to the north, just to the north of the equator, and to the south, just to the south of the equator, that means water is being pulled away from the equator on both sides, which means water has to come up from below, because wherever you have water being removed, new water has to come in. So here a wind was coming together and rising into the atmosphere, whereas in the ocean currents are moving away from the equator and water is coming up to the equator. That's called upwelling, and I have podcasts on that if you can follow up. And funny things happen when you do that. You can think of Galapagos Island, which is here, and waters are being pushed to the north and south, and waters are being diverged or moved away from the equator. Cold waters come up, they are full of nutrients, so Galapagos is full of phytoplankton, zooplankton, fish, diversity of biodiversity as we call it, iguanas and penguins and all kinds of dolphins, fish, animals, and so on and so forth. What is Galapagos also famous for? Charles Darwin, the father of evolution as we know it, actually was sitting on this island for 3 months as his ship, the Beagle, was going around the planet, and he used to get very seasick, and so he was very happy to find land and stay there. And when sitting there and looking at all the birds and the animals, he had many ideas about how evolution happened in the past and how it happens. Okay, so that's the Coriolis effect. You can learn more on your own if you're interested and if you can understand the details, but I will leave it here. You just have to remember that things are moved to the right of the direction of motion in the northern hemisphere, to the left of the direction of motion. To the direction of motion is critical to remember. Okay, east, west, north, south, it doesn't matter which direction you are moving, it will be pushed to the right of your direction of motion in the northern hemisphere, to the left of the direction of motion in the southern hemisphere. So let's leave this here. We'll come back and do a little bit about water cycle and carbon cycle. We mentioned elemental cycle in the last chapter, last section, and carbon is one of the elements. As we said, there are also nitrogen cycle, phosphorus cycle, iron cycle, and so on. We'll just learn the example of the carbon cycle here. Okay, see you in the next podcast then.